Hello and welcome back to AP Physics. So today we're talking about power, and power is the rate at which work is done. What would a rate mean in this case, or from that may matter any case? Uh, Rate is how quickly something can be done, or in other words, it's that quantity divided by time. The power is equal to work divided by time. Work is in joules, time should be in seconds. And so therefore power will have units of joules per second, which is also nicknamed a watt, which the symbol for is a capital W. And also, since work is also equal to the change in energy, power is also equal to the change in energy over time. So keep that in mind. And what a watt really works out to in terms of base units is kilogram meter squared per second cubed. So which is more powerful, a motor which can do 100 joules of work in 2 seconds or one that can do it in 1 second? Well, the motor that can do the job faster is going to be more powerful, even though they do the same amount of work. Now, a watt is a joule per second. A kilowatt is equal to 1,000 watts, which is equal to 1,000 joules per second. So you should be familiar with the term watt as in light bulbs. A 40-watt light bulb, at least an old school 40-watt light bulb, we used to use 40 joules of energy per second. And a 100-watt light bulb was brighter because it used 100 joules of energy per second. Compact fluorescent lights and LED lights use much less energy, use much less of a power requirement to produce the same amount of light. Sometimes they're still rated in watts, like 40 watts or 100 watts, but they actually don't use that amount of energy. Your electric meter is dialed in kilowatt hours. So they multiply the kilowatts times hour, which gives you energy or joules of energy that's used. So it could be there's a conversion between kilowatt hours and joules, because they charge you on how much energy you use, not the rate at which you use it. So if you walk up a set of steps, you change your gravitational potential energy, and you do work. If you run up a set of steps, if you run up the same set of steps, you do the same amount of work, the same change in potential energy. But in order to run up the steps, you need to do it more quickly, and that requires more power. Here we've got two motors. They both do the same amount of work, but the larger motor is more powerful. It can do the same job more quickly. So what is the same here? Are these motors doing the same amount of work, the same power? Well, this motor lifted a 10 kilogram mass up in the same time this lifted up just a 1 kilogram mass. So this one motor did more work in the same amount of time, and therefore it's more powerful. What about here? Which motor is more powerful here? At first you might say it was the same. Then this one stops and this one keeps going. Well, they're both doing the same rate of work. This one just does twice the work, but it also does it in twice the time. So they both have the same amount of power. Okay, so a 35 kilogram box is lifted from the floor to a height of 2.3 meters in 3.0 seconds by a forklift. What is the power of the forklift? Well, power equals work divided by time, and work equals the change in energy. And the type of energy that's being changed here is gravitational potential energy. So the symbol for that is, or the equation for that is m times g times h. So plugging in our mass is 35, gravity is 9.8, and height is 2.3 meters. We do 788.9 joules of work. Now to figure out the power, we've got to take the work that we did and divide by time. And so we divide that by 3 seconds, and we get 263 joules per second, or watts. Now, if we had a motor that was twice as powerful, it could have done that job in half the time. Okay. What power requirement for an engine would be required to accelerate a 2,700 kilogram car from 0 to 15 meters per second in 10 seconds? Well, power equals work over time, and work equals the change in energy. The type of energy that we're dealing with here is kinetic energy. So we're taking it from 0 joules of kinetic energy at 0 meters per second to 15 meters per second, and however much kinetic energy it has there. So the work is going to equal the kinetic energy that it has at 15 meters per second. That's 1/2 times mass, which is 2,700, times velocity squared. So don't forget to square 15 squared. And we get that the work is equal to 303,750 joules. And to figure out the power, we just take the work or the change in energy and divide by time. And then we get 375 watts. And working another problem, number 13, here we've got a motor that's rated to do 60 watts of work, so 60 joules of work per second, and it's going to lift a 50 kilogram student upwards at a constant speed. What would the upward vertical velocity? Well, power equals work over time, as we did before. And work is going to equal the change in energy, which is going to equal the change in gravitational potential energy, which is mgh. Now, if we plug that in for work, we get power equals mgh over t. Now, the height divided by the time is the upward vertical speed. It's the velocity. It's the rate at which its height is changing. So that's my velocity that I'm looking for. So we can reword this as power equals mgv, where 60 watts is equal to my power. My mass is 50 kilograms. Gravity is always 9.8, and we solve for the v, and we get that the velocity is equal to 0.122 meters per second. Another way we can talk about power, another unit, is in horsepower. So basically, horsepower was, I guess, approximately equal to the rate at which one horse could do work. It was lifting a 330-pound weight up 100 feet in 1 minute. It's defined as a horsepower. And a horsepower in terms of watts is equal to 1 horsepower equals 746 watts. So that was something you might come in handy to have, but nothing you need to memorize. Skip that. Okay, and that's it for today.